Let's talk about uncertainty in deep learning, which is really important. So my favorite is wavelet neural networks because I'm from planet Saturn, but let's skip it because we still use those PyTorch and TensorFlow and the classical deep learning. This thesis is really important, and it is in 2016, but it's a good review of the uncertainty in deep learning, and I learned a lot after I read this thesis, this amazing thesis. So, is the model certain about an output? Should I change the model? And I give you with an example. But here we use regularization to avoid overfitting, as you know. So some regularization and a cost function. Here, this is. But there are different kinds of uncertainty. But the most important one is epistemic or model uncertainty. Episteme in philosophy, I think it is knowledge. And here we mean knowledge, we represent knowledge by model. And the uncertainty of the model, model uncertainty, it relates to that sometimes we don't have enough the data. For example, we are using it wrong. For example, look at this. If you use classifier 1, you can distinguish cats and dogs. But a random rabbit is an out of distribution test data for classifier 1. It hasn't seen, so it becomes something like this. It's a random rabbit because it hasn't seen that. So most of the time, it has seen the classifier 1 has been trained on cats and dogs. Cats and dogs are around here. So it is trained to be like this. And suddenly, I give you this point, which is not trained because this is a rabbit. So the rabbit cannot be classified. So it should say that this is uncertain. It should say that this one has big uncertainty because it has not been trained in these types of data. So we ask if it recognizes a rabbit, and we want to show uncertainty. And we don't want to extrapolate at any cost because, if you extrapolate in an application like self-driving cars, somebody kills, somebody dies, and it's very bad. And in healthcare is bad as well because you don't want to, for example, kill a person with a drug that you have discovered. So it's very dangerous. That's why model uncertainty should be the focus of the researchers in deep learning. So always show uncertainty. And the model uncertainty, as I said, is like we call it epistemic uncertainty. And there are other types of uncertainty as well. And aleatoric uncertainty, it's an irreducible uncertainty. And model uncertainty, which is reducible uncertainty. And the applications to AI safety, as I said, for example, self-driving cars in healthcare and those things, we have lots of problems like distributional shift, like negative side effects safe explorations, and each of them is a huge topic. And there are other applications of model uncertainty. For example, in active learning, you want to rank points based on their potential informativeness. You want to actively, for example, find which one should I label or not, or those things. And if you have some information about the uncertainty, you understand which one is safe and which one is necessary to go through labeling and those things. And there are stochastic regularization methods such as dropout, which I really like, by Geoffrey Hinton. The other one is multiplicative Gaussian noise, drop connects, but all of them are quite similar to each other. And let's review the Bayesian modeling. As you know, we use softmax likelihood, and our posterior has typically some problems because the denominator of that is intractable. And just for a very simple, trivial example, you can calculate an explicit form of that. But in general, it is intractable, and I tell you how to approximate it. So this is intractable. That's why the posterior becomes intractable. So intractable marginalization, you have intractable posterior. This is your posterior because the weights of neural networks, these are the weights of neural net. You want to know what if after training, what happens to the weight? Because first of all, you say, okay, they have some prior on your neural network or deep learning. For example, you might say, billion parameter, you put a prior on a billion param. You mean you have billion priors because you have billion parameters, and you have seen the function space as a parameterized function which has billion parameter. And I tell you, that's not the way. That's not the way we should do in the next 10 years at least. So approximate it using this Q. And as usual, they factorize it because it's simple, everything that is simple. And so they factorize it. So as usual, we want to minimize KL divergence. And as you know, it means that you want to maximize the elbow. So you want to maximize the elbow, and here, of course, we should integrate over all dataset. It's a problem. That's why I use some other techniques. So Bayesian neural network, as I said, you have a distribution over weights. This weight is not fixed. You have a distribution. You randomly pick that. And so there are two methods. Frequentists use just ensemble methods, and the Bayesian approach is quite tough because you write the equation, you think about each equation very deeply, and finally you try to very intelligently minimize and simplify your equations to be solved by a simple stochastic gradient descent method. And we minimize the KL divergence, as I said. As I said, we usually use factorization because it's simple, not because it is the true things. Of course, it is not good to always use normal distributions. Sometimes it is better to use exponential family. I think that guy, Hoffman in Google, introduced the use of, popularized exponential family instead of just simple normal distributions. And description length is things in communication theory and information theory, and nowadays in machine learning and other areas. But it's just another way of writing this. Another way of writing this. So it's a summation of this and this. And the first term is not tractable. So we use Monte Carlo. I mean, this term is not tractable, this integration. So we use Monte Carlo integration. We sum it, and we have many samples, so we take the mean of that and those things. The other problem that we have is this performing summation, because in big data you have billions of data, for example, and n is large. So we should do techniques like batching and those things, subsampling and those things. And stochastic variational inference, and this is the typical algorithm. And I really care about the method of Hoffman. You can read his article. It's about, I think, 30 page or 40 pages, but it's worth reading that. Compute expected likelihood derivative for optimization process. Of course, there are three methods. Character function, which has the least variance, which is a very good method. The other method is past derivative, but here I'm just focusing on score function. In a score function example, we use this fact, and we simplify this integration, because after all we should compute it, because we need to optimization, so we should know the gradients of that. So the score functions become this, but they compared and found that this method works well because it has least variance. And this article is really practical, as the name suggests, because you have many methods for variational inference, but this one is very simple. And so, as I said, this minimum description length, MDL, this loss function, we can write it as a complexity loss and the error loss. And again, you minimize the variational free energy. And again, you factorize it because it's simple to factorize things. And so this is your loss. So for different choices, prior and delta posterior, for example, if your prior is Gaussian, you get this loss. If your prior is Laplace, you get this loss. And again, for posterior, if your prior is Gaussian, then this is your loss, and your gradient becomes very simplified. And finally, the optimal parameters can be calculated. So the maximum likelihood is not the best one because it has an error of 27, and the adaptive weight noise has a smaller error, 23. And the other one that I care is just a simple adaptive mean L1, which is 25. So it's between maximum likelihood and adaptive weight. The future depends on some graduate student who is deeply suspicious of everything I have said.